Hello, I'm Stijn Van Der Perre, and I work at the Brussels School of Governance, which is a part of the Vrije Universiteit Brussel. Within this group, I work for the Center for Environment, Economy and Energy, where we have expertise in EU and national low carbon transition policy. And today I will present my work on the modeling of carbon flows in the value chain of packaging plastics, which falls under the Precura project. So as you all know, carbon is a central and main element in polymers, in plastics, and 90% of this carbon is fossil-based. And at the present CO2 intensity of plastics, greenhouse gas emissions will rise spectacular if the plastic production and use grow as currently planned in 2030 and 2050. They estimate these emissions could reach 1.3 and even 2.8 gigatons CO2 a year. So in the context of reducing the CO2 footprint, and in the context of the transition of a linear towards a more circular economy for plastics, we performed a kind of thought experiment, how long carbon is now embedded in plastics and how we can improve this by extending the lifetime of the residence time of carbon in plastic materials. So in that perspective, a carbon study was performed to map and to evaluate the carbon flows across the value chain of packaging plastics. And then in the next phase, some innovative technologies and processes were included with the idea to, or with the goal to maximize the carbon content in relevant products and minimize the carbon leakage to the atmosphere in the form of CO2 emissions over multiple life cycles. We focused on packaging plastics because packaging is the largest end-use market for plastics, and those plastics have also a short use cycle. So different case studies were elaborated. We have a base case or a business as usual case, which acts as a benchmark and represent the conventional technologies which are used to produce polymers from a fossil-based feedstock with the current waste management technologies, such as mechanical recycling, incineration, and landfilling. In a second case, we have an electrified naphtha cracker. We then focus on an optimized high-value chemical yield and also an improved end-of-life treatment, which means also including other types of recycling, such as chemical recycling. This is called the ELEC Plus route. And then in the third case, we start from a bio-based input and also include the chemical recycling techniques. So here a process flow diagram of the value chain of plastics is shown, where we start from a fossil-based feedstock, which is mainly a naphtha feedstock, which is cracked to high-value chemical yields. High-value chemicals in this are mainly ethylene, propylene, and the aromatics, benzene, toluene, and the xylene isomers. And these high-value chemicals are used as monomers or used for the production of monomers, which in turn then are used for the production or for the polymerization to end products. These end products, they have a certain life time, and after their use phase, they can be recycled via a mechanical way or a chemical way, which closes the loop. So in these industrial processes, we look at two important parameters: the carbon efficiency, which is the amount of carbon in the output in relevant products divided by the total amount of carbon present at the input. And a second parameter is the energy footprint. And all these data is retrieved from mass balances of real processes or simulated processes found in literature. So as end products, we focus on the packaging polymers, which are mainly polyethylene, polypropylene, polystyrene, and the PET fraction. Also, of course, during the cracking of naphtha of other feedstock, also other molecules are formed. We have a C4 or C5 fraction, for instance, butadiene, isoprene, isobutylene. These can be used, for instance, for the production of rubber polymers. And during their use phase, a time factor is introduced, and this allows us to calculate the residence time of carbon in packaging plastics. So during the study, also some assumptions were made. For instance, the lifetime of packaging plastics was set at 6 months. For rubber polymers, which can be used, for instance, in car tires, they have a longer lifespan, and for instance, this can vary between 5 and 10 years. For mechanical recycling, we assumed closed loop recycling, which means that a PET bottle is recycled again to a PET bottle, which in reality is a minority. For chemical recycling, a solvolysis method was used for the PET fraction. The remaining was thermal cracked via pyrolysis and/or gasification. And during the recycling, we did not consider the presence of plasticizers or fillers or pigments, which might complicate the recycling process. So here a general overview of the different cases are shown. In the first case, we have a naphtha feedstock. We have a conventional naphtha steam cracker. And in the end of life treatment, an average recycling rate for packaging plastics is used in Europe for around 45%. Only mechanical recycling was used, and the remaining plastic waste was incinerated or landfilled. In the second route, an electrified cracker was used, and in the last case, we started from a lignocellulosic biomass input, which generated a different polymer output. Also polylactic acid and polyamide 6 were produced in addition of polyethylene and polypropylene. These two cases had both an extremely high recycling rate and almost ideal recycling rate of 95%. So both mechanical as chemical recycling was applied, and also CCU was implemented on the incineration of recycling and sorting loss. Also to mention that both cracking processes were simulated by the group of Kevin van Geem, so big thanks to them. And also the fractionation of the biomass input was based on work found in literature. So if we go to the result section, so first Sankey diagrams were developed for the production phase. Where we see that in the second route, we have the highest amount of polymer output. This is, of course, we optimized the high-value chemical yield by having a switch from the fuel products to more chemicals like the olefins and aromatics, which could be used for the production of polymers. For the bio route, we see that this route is the least efficient one. This is also because it's very the input is much more complex than in the other two cases. We also made some Sankey diagrams for the end of life phase, where we focused more on the CO2 emissions, where we see in the first case, in the base case, that about 2/3 of the carbon present in the packaging, in the waste packaging, is converted to CO2. Well, this is much more limited to 10 and 15% in the ELEC and the bio route due to an improved recycling or end-of-life treatment mechanism. So if we look at the residence time of carbon in the plastic materials, we plotted the carbon content in packaging polymers as a function of the time. The idea was we started from a certain amount of carbon, and then we see how long does it take when all or almost all of the carbon in the plastic materials has dissipated. For the three routes, we see a clear exponential decay, especially for the base case, where after between 2 and 2.5 years, less than 1% of the original amount of carbon was still present in packaging materials. The remaining carbon ended up in the form of CO2, which was released to the atmosphere. So because all those three curves had a kind of exponential decay, we did a fitting of these points, and this allows us to quantitatively compare the three cases via the carbon half-life time. For the base case or the bar case, this was only a couple of months, while this is a couple of years for the other two routes, which a difference of a factor 5.5 and 7. We didn't only look at the carbon efficiency, we also looked at the energy footprint. This was also monitored for the production phase and the end-of-life phase. The difference in the production phase is mainly in the cracking and processing part, especially in the ELEC route to optimize the cracking byproducts or by optimizing the yield of the high-value chemicals. In the bio-based route, of course, energy-intensive processes are needed to obtain a good monomer output. For instance, the fermentation process of lactic acid is quite energy intensive. For the end-of-life phase, a major part is allocated to the CCU, which is implemented on the incineration, and the carbon dioxide is hydrogenated to methanol, which can then be used again for the production of olefins and aromatics, but 90% comes from the production of hydrogen needed to the CO2 hydrogenation. And another important part is allocated to the chemical recycling, which is also much more energy intensive than mechanical recycling. So just as a quick conclusion, so from the first findings, we see that there is a considerable loss of carbon over a relatively short time period. even in the ideal cases with a very high recycling rate, we see that only chemical recycling is not the holy grail, but for sure an added value. The model gives also a good view on the energy demand and the carbon loss via CO2, which translates in a clear trade-off between carbon circularity and the energy footprint. So how to improve maybe the carbon in products? We can apply more CCU, but this will also cost extra energy. On the other side, we can also extend the lifetime of the products itself via the use of reusable PET bottles, and this can also be combined via a deposit scheme. So for future work, we would like also to expand the recyclability to other polymers, for instance, the rubber polymers, and maybe we also wanted to combine some case studies, for instance, the input of biomass to compensate for the carbon loss in the electrified route.